Okay, so it's my pleasure and honor to chair this afternoon session. We will have two talks during the session, and the first will be given by Professor Rainer Blatt on the quantum way of doing computations. Rainer.
Thank you very much, Jean-Michel. Good afternoon, everybody, and welcome back after lunch. I would like to share with you a few ideas how we can actually do quantum computations. And what I'm going to talk about today, was I've already advertised, is ion trap work. I cannot use the laser pointer, so I'm just sticking to the old-fashioned part of doing this. This is the ion trap that we use, the device, to isolate in space a few atoms, which serves then as the quantum bits for the storage and the manipulation of the quantum information. I'll come back to that in a minute. So the menu of today's talk, of this afternoon's talk, first one, is that I would like to talk briefly, very generally, about computers and technology, and then I would like to address the question, why do we actually want quantum computers? Then we go into bits and pieces. In particular, these are quantum bits and quantum pieces like quantum registers, quantum gate operations that we need in order to realize that, and a few thoughts about realization concepts, how we can actually do these things. And then I would like to delve in the second part of the talk into what we do in Innsbruck, quantum computation with trapped ions. I will show you first the toolbox with these ions, and then as an example, just two things: quantum simulations in both analog and digital fashion, and scalability of the ion trap. I leave then to Dave Winan, who is going to talk about this later in more detail and more about the technical applications. So this is all work that was done at the University of Innsbruck in conjunction with the Institute of Quantum Optics and Quantum Information of the Austrian Academy of Sciences. So let's get started. And I would like to start with some famous people, with some quotes here. If you just look back in the year 1949, you find in the American magazine Popular Mechanics a remark where a calculator on the ENIAC is equipped with 18,000 vacuum tubes and weighs 30 tons. Computers in the future may have only 1,000 tubes and weigh only 1.5 tons. Okay, so this is not that far back. It's a little older than I am. Even in 1986, nobody else but Richard Feynman actually said we ought to be even more ridiculous later and consider bits written on one atom instead of the present 10 to the 11 atoms. Such nonsense is very entertaining to professors like me. I hope you'll find it interesting and entertaining also. I would love to keep you entertained for the next hour. Let's see if we can do that. And what we all know now today is the progress in technology is very often measured in terms of Moore's law. Gordon Moore is one of the founding fathers of the Intel Corporation, and he started noting in more or less empirically in the 60s that the computer power in those days, actually the electronic power of these systems, increases over time. And he empirically formulated this law, which is now not so much a surprise anymore, that he just draw the line here, transistors per die as a function of the year in the semi-logarithmic way. And you see this slope is such that today we have the claim that the computer power doubles every 18 months, usually by miniaturization, and such that the system also becomes smaller. This is not by chance, because after this was formulated empirically, of course, people had to think about how to make these devices that allow you to make these the electronic devices smaller and smaller. So it was paving the way in terms of a roadmap for the semiconductor industry for several decades. And the question is, can this still hold today? And I have here other data that I assembled from this person, Richard Keyes, Rob Keyes, from IBM, that he published in the late 80s, but I calculated a few things more. Here we draw the number of atoms that you actually need to implement a classical bit of information. And if you draw that in the semi-logarithmic way, as the same way as Gordon Moore's law, then you see that, of course, initially this starts out with about the 18 atoms in the 60s, and goes down all the way to the point that the Pentium 4 in 2002, that's pretty much still on the line, but then it goes off, and the recent released 14 nanometer transistor shows that it's away from that line. If you were simply extrapolating this, then of course right about now, then a single bit of information would be written on a single atom. And the question really is, can we actually do this? And we have seen for last year, of course, there was an article in Nature magazine about the end of Moore's law, or actually this was more formulated more than Moore. Can we actually do more than that? And here it shows the current fate of this. This still seems to be going on right here, but when we just look at the speed and the density of the chips, the transistors that we have, they roll off and this is going to stagnate. So in other words, Moore's law is going to come to an end. And of course, long before that, we have to invoke the laws of quantum mechanics. So the question really is then, why do we want to have quantum computers? Now, the generic answer for that is simply there must be applications in physics and mathematics, but what are they? The entire hype that we are seeing these days started around about in the mid-90s when Peter Shor from AT&T came up with an algorithm where he could show that if you had a quantum computer, then you could actually factor numbers with L digits much faster than in a classical computer. The reason for that is simply in a classical computer, these numbers have a certain length L, and the efforts that you require in order to factor them grows exponentially. On a quantum computer, due to the superposition principles that are working there, you get a scaling law which is only polynomial, namely L squared. And a little later, Lovrolo from Lucent came up with the optimization algorithm where he could show that even this search in a database, an unsorted database, could be split up by the square root of the number of entries that you have here. So there's applications that are still some of the most important ones, but there's also something that Richard Feynman already pointed out. This is the simulation of Schrödinger equations, because as Feynman said in the 1980s, the computation of Schrödinger's equations of quantum mechanical problems on a classical computer is going to be hard and tricky because you have to store all the superpositions. If you had, say, underlying quantum mechanical elements that store these superpositions automatically, then it would be much nicer to do that, and he already hinted to doing this, but there was no way in those days to do it. This is nowadays one of the hot topics, and I'll come back to that at the end of my talk. Something else that is probably long forgotten, but is not so emphasized very often. This is spectroscopy, or what I call the quantum computer as an atomic state synthesizer. As Dave Vineland and his group have shown in one of these papers there, if you really have a quantum state, then you can tailor it, because you can manipulate atoms in such a way that it is really best suited for a certain measurement. So metrology is one of the key issues that we have, which can be improved with quantum methods. And like we have very many sensors in our world, quantum sensors will certainly be able to enhance these things quite a bit, and David is probably going to talk about more about this in the end. And something that I usually tend to say, but we can substantiate that later, is we now look at quantum physics in hindsight with what I call the information-guided eye. This is something different. What do I mean with that? If you had talked to me, for instance, 20 years ago, then I would have said, okay, if a quantum jump, you heard about this morning, happens, this destroys the quantum information immediately. There's just no way to do it. But we know from computer science there's the notion of error correction. And this can be carried on to quantum science. We can do quantum error correction. And we can just use some of these ideas now to do this. On the other hand, in hindsight, now we can just look back in quantum physics. We can just apply similar concepts like Shannon's entropy and all the information things that we look at that. So it's a renewed view, and I also have to admit this is something I did not foresee, which I think is now one of the major advantages. I don't have the time to go into this more fundamental point, but we can discuss this maybe later on. So there's a number of reasons why we actually want to have quantum computers. The question is how to do one. This was nicely summarized over the mid-90s to the end 90s by David DiVincenzo, and here is one of the papers that I cite here. He came up with several criteria a system has to fulfill in order to be suitable for a quantum computer. First of all, you want to store your information. So you have to store the information in so-called quantum bits, qubits, and you better have a scalable physical system with each quantum bit well characterized. Secondly, you want to be able to start from an arbitrary initial state. So you have to have the ability to initialize the state of the qubits. And then, of course, in order to break down an algorithm, you have to have a long coherence time, which is much longer than each individual gate operation time. Then, of course, you want to be able to make universal quantum computations, so you better have a universal set of these quantum gates. And finally, you want to read out this result into classical information, so you need to be able to measure your quantum system in such a way that it reveals that classical information with high reliability, or as we say today, fidelity. And he a little later came up with two more of these criteria. In order to do some networking, you first of all need the interfacing function. So you need to have the ability to interconvert stationary quantum information which is stored in the qubits into flying qubits and to convey it to a different location. So you need also the ability to faithfully transmit these flying qubits between these different locations. I call this today the 7 commandments of quantum computing. So if you really want to check another system whether it's actually able to do this, this is a very good starting point. So let's see how we can fulfill them. First of all, we need quantum bits and registers. A classical bit, of course, is all known to you. It's nothing but a physical object which is either state 0 or state 1, up or down. There's nothing else. And then there's registers, as we know from a Pentium, a 32-bit register, is nothing but a bit row of zeros and ones, or elements that can store zeros and ones. A quantum qubit, a quantum bit or a qubit for short, is a superposition of those two orthogonal states in a quantum mechanical sense. So we just write this down as an old-fashioned two-level system with these amplitudes that we have there. And of course, in a pictorial representation, we usually represent this in terms of a Bloch sphere. So the North Pole and the South Pole would be the classical switch positions, but for a superposition, it could point anywhere in between. We don't know where it is. We would have to measure statistically and find out what the C0s and the C1s are. And the quantum register is then the generalization of that. We have then a row of these two-level atoms. But here comes the difference. Instead of just having independently operating bits like in a Pentium, we have to write this down as a direct product. So in other words, we can take the superposition principle beyond, say, spatial distances, so we just entangle the system. In other words, we have to write down the quantum state of the system in such a way. So unless different from what we do in the classical way, if we just do something here on the last qubit, then of course this will change the entire state, whereas in this case it just changes the last one. Suppose I just add 1 to the 0, I get a 1. 1 plus 1 is a 0, I keep 1 in mind, then go to the next one with the carry, and so forth. You just have to do this. Whereas here, if you do an operation, the entire space is affected because of the entanglement feature that we have there. And so we have to write down the general state in the superposition, and this is what's called these days quantum parallelism. So in other words, quite different from a classical computation, a quantum computation is generating and manipulating interference patterns in a computational space. That computational space, of course, takes place between all of these various interference paths that we have here. And if you just add to this, and they say already for 62, 64 bits, or qubits in this case, we have about 10 to the 19 interfering paths. I'll show you later an example how this works. So you really, by changing a single element there, you're really changing the interference pattern. It's a different paradigm than a classical computer. Something that's always mind-boggling to me is if you just consider that, for example, only 300 qubits, that would really mean that the number of these computational pathways exceeds the number of atoms in the universe. I personally have no idea what that means. We can come back to that in the end, because I personally think there is something to gain from if you could control the subspace, or we know if what calculation happens in which subspace. This is something which is unexplored. This is what we do, and that actually shows you the power of a quantum computer. But let's go back now to the operations. Suppose we had then, according to the De Vincenzo criteria, these qubits. Then what we need is a set of gate operations, a universal set. First, we need so-called single-bit operations, which really means we have to be able to position the quantum information in arbitrary input states. So we have to be able to position that error at any position there on the Bloch sphere. And we have to be able to rotate that single qubit about any arbitrary angle that's there. This is fairly simple. I don't show you the details, show you how later it works. By interacting, let atoms interact with radio frequencies or with laser beams, so we can do that. More importantly, as was pointed out in the mid-90s, we need operations between two qubits. And this is analogous to the classical XOR operation, the Boolean XOR operation. But it has to work this is the truth table for the XOR, in a way which is quantum mechanically valid. And you see this already from the Brown-Kett notation that I've written down here. What it means is the following. Suppose you have a controlling bit which has an excited state amplitude. Then, once there is an excited state amplitude, then it's supposed to flip the state of the target bit. But that has to hold not just for probabilities, it has to hold for superpositions, so for amplitudes. And that's the real hard part. And that took us about 7 years to realize in our lab. But the good news was, and that was already known in the mid-90s, together these two operations are already a universal set. Once you have realized that, in principle, you're allowed to construct a full-blown quantum computer. So let's go for it. In other words, once this is known, I have a blueprint, a recipe already, how to make a quantum computer in principle. So we start out from a superposition on the left-hand side right here, and then we have a process, I'll come back to that in a minute, and we end with a superposition. That process, as we just learned, can be broken down in a sequence of single and two-qubit operations of the C0 kind. And of course, this is a large unitary matrix that we could write down, and since it's unitary, I could reverse the process, could go back. I haven't gained any information. So let's go forward and get the information, but in order to get the information, I have to measure that register, so I have to project it to its eigenstates, and then I get the classical information. And this is then the task that we have to do. So you have to have an input, you have the output, the classical measurement, and in between we have to realize the computation as a sequence of these quantum gates. Now, what are the realization concepts? Over the last 20 years, many of these have happened. This is only about 10 of them that I've listed down. I think it's about 15 or 18 different technologies that have been explored. If you want to look it up, there are so-called roadmaps formulated for quantum information processing. That's the US roadmap, which is no longer continued, but still has some valuable information in terms of the DiVincenzo criteria. And there's the European roadmap, which is slightly wider formulated and which is still continued. And without going into the details here, ion traps I'm going to talk about later on. There's also neutral atoms that hold qubits, optical traps, lattice, and so forth. Neutral atoms and cavity QED for conveying information. We have seen some of this in the morning already from Serge Rochstork. NMR and liquids, superconducting qubits, and so forth. I don't want to go through the list because I'm not going to talk about this. Over the last 10 years, it has pretty much, I should actually say, all of these quantum systems must be able to, must be controlled and manipulated. You must be able to do that with a high fidelity. But over the last 10, 15 years, it has been shown predominantly that these techniques survive so far. There are others that may still be suitable, but they have some drawbacks, are no longer technically so favorable. It's ion traps, there are some neutral atoms and traps, there are superconducting qubits, we've heard about this morning. We won't have the opportunity to hear more about this. They come in various flavors, and there's other solid-state concepts like spin systems and quantum dots. So let's just look at these technologies, and in particular, I will concentrate now on the ion traps. The ion trap concept was formulated for the quantum computation by these two people, Ignacio Cirac and Peter Zoller, who had this seminal publication in 1995, where they proposed essentially how to make the C0 gate operation of this kind. Because that's the very hard part. The rest was pretty much known. You just take the ions in a trap, have them sit side by side. I'll show you that in a minute. Address them with a laser for individual qubit operations. But how to make the if-then decision with the C0 gate operation, if there's an excited state amplitude, how to make a rotation on the target qubit. And in the meantime, there's many more gate operations, also by Cirac and Zoller, some by Mermer and Sørensen, Jared Milburn, Nishin Saguri, and Enrico Solano came up with pretty much the same idea around the same time. Jonathan Blenio and Knight came up with light shifts gate. We have geometric phase gates, also gates operations by Didi Leifert and Dave Wineland were put forward and shown in those days. But let me just concentrate on this for a minute, just because it was the seminal idea. Before we do that, so let's first, according to the DiVincenzo criteria, come back to the qubits. The qubits that are available with these ions are essentially our two-level systems. The two-level systems come in various flavors. Of course, as you all know, the two-level systems exist only in theory. In real life, you have to make them by optical pumping, and you have to do something for it. This can be done, for example, in all these alkaline earth atoms, which are hydrogen-like. For example, there's optical transitions between low-lying states. That's a stable state, that's a metastable state, and this could be used. We have seen the 3-level systems this morning. Or you could actually use in the hyperfine structures these 2-level systems right here, and using Raman transitions or even Zeeman transitions. All of these have been used, all of them in blue have been used for quantum information processing. So these would be the carriers of the quantum information. What would be the carriers of the bits? These would be traps. What are these traps? These traps all derive technically from what's known as the Powell mass filter from the 50s, where Wolfgang Paul showed how to guide a beam stably through the electrodes if you just provide the right frequencies with the right voltages in a mass selective way. Now you can keep the ions inside by winding rings around it and keep them in the center. Or you just replace the rings by these segments. You see, this was developed in Innsbruck and Ann Arbor. This was developed in Boulder mines by the Dave Weinland's group, by Günther Wert, and also Nahut by Michael Drevson's group. And we have this kind of a trap developed, and we are still using that one. There's all kinds of mixed traps, and I'll show you other traps later on. And David Weinland is going to show you even more segmented and the traps of this kind. The trap that I'm talking about today is essentially that one. This is the trap that we've been using since around 2000. Just to give you an idea, the distance between these tips is about 6 millimeters, and the lateral distance between these electrodes right here is about 1 millimeter. But it suffices to say, this is actually providing a harmonic potential, that's a harmonic oscillator, for these trapped ions, and this in particular for calcium ions. And this is, of course, described with 3 frequencies. The frequency along this axis, this is the z-axis, is about 1 megahertz. It can be changed between 0.7 and 2 megahertz, depending on the voltages. And laterally, the x and y direction is about 2 megahertz, as is indicated right here. So that's all that needs to be remembered throughout the talk. How does now the Sirac-Sola idea actually work? We have the quantum bits stored in either the optical transitions or the ground-Zeeman coherences, and we have the ions sitting in the trap side by side. Such a quadrupole. Most important part of the Sirac-Sola idea is writing down this state vector. What does that mean? That state vector is decomposed in the internal degrees of freedom. This is the individual information of all the 2-level systems that you have here, times the center of mass motion. And the center of mass motion is supposed to be initialized in n equals 0. What does that mean? This is a harmonic oscillator of the chain that moves. And n equals 0 really means the ions are sitting there stock still. They are not moving at all. The idea of Sirac and Sola was the following. Suppose I have here my ion that is supposed to control the state of that ion, but its amplitude is supposed to control that. How does this ion know that there's an excited state amplitude? The idea of Sirac and Sola was, okay, let's just point the laser to that ion, make a transition in such a way that the information of the respective ion, that would be ion number 2 right here, is written to a 1 of the center of mass motion. In other words, we transfer the internal degree of freedom to 1 phonon of the vibration. Now the ions are charged, of course they're repelling each other, and the single ion, of course, starts to move the entire chain. From the point of view of the chain, of course, the chain doesn't know where the phonon was put in. This not knowing can be described as entanglement. So we are entangling the internal degree of freedom with the external degrees of freedom. Now we just go to the second one and make a transition. I'll show you how to do this in a minute. If and only if there was a motion by spectroscopic distinction. And that's done, we go back to the first ion and we take that information, the 1, back to the internal degrees of freedom and leave the system alone. So we just restore the system according to this truth table. That requires, of course, that we individually address these ions to these single qubit operations in an efficient way. Of course, during the operation of this, we don't want the system to decohere. And finally, we have to realize an entire quantum computer by a whole series. There's a sequence of these laser pulses. So these are the tasks at hand that we have to do. And this is the system that you have seen this morning. This the system as this right now. If you want to know more about this, is the latest status of all the system. Is this linear trap. You can store up to about 20 ions in such a system, cool them with these laser systems, and then, of course, individually address them with these systems there. And you can routinely see strings of 15 or so. That's how we work with typically in our lab. Now, what is the system? You have seen this level scheme this morning. as well. The qubit is implemented here in an optical transition between the ground state S1/2 and the excited state D5/2, which is long-lived, about 1 second. And this is, of course, in the spin notation, spin down. This is our spin up. And this can be seen by shining laser light on it. On this dipole-allowed transition, as soon as the atom scatters light, it gets, of course, projected to that state, and then it's bright. And if it doesn't scatter light, then it was projected to this state and doesn't scatter light. So this is what we see in mathematical terms. This is a sigma z measurement. Okay? Now, we can detect, of course, quantum jumps. You have seen this morning. But you can do this also for a full chain. And for instance, for a chain of 4, we can all see these things when we can easily discriminate, okay, there's 3 excitations, 2 excitations, 1 or 0 excitations. All 4 are bright, and we can make electronic distinctions, so we can just know how many of them are bright, and from the camera we know even which one is bright. So let's summarize. We have in our system a 2-level system, which is written here, and we have the trap, which is, of course, quantum mechanically just a harmonic potential. Now, keep in mind, we have to rewrite this as a series of 2-level systems, which are just different by the trap frequency. That's this difference right here in energy. So we denote these systems with the quantum number of the harmonic oscillator and the ground and the excited states of the electronic excitation that we have in the system. So we have various 2-level systems, what I call a ladder system, which of course gives us the chance with the laser to shine in different frequencies. If, for example, if I shine in the laser only on this one, then of course it makes predominantly transitions between the excited state and the ground state, and maybe once in a while it goes there or goes there, but on average doesn't do very much. But I could also shine the laser, for instance, right here. Then it predominantly decays on this state and climbs down the ladder until it resides in n equals 0. This is the optical pumping process, which we call sideband cooling, and that was referred to by Serge Roche this morning, so we end up in that state. Once it's there, one can show that due to the minute amount of motion that it still has, there are only 3 transitions allowed. This is what we call the carrier transition. And there's this blue sideband transition, which is just long by 1 phonon frequency, and the red sideband frequency, which is just short by 1 phonon frequency. And these 3 transitions are now used to manipulate things. Remember, for the Dirac-Sola idea, we need to make transitions which add or subtract 1 phonon. We add 1 phonon it was, or we take 1 out. This is precisely what we do with these sidebands. So we create the entanglement, and with the internal transitions with the carrier, we just create the entanglement, the superpositions in the internal qubits. So these are the basic operations that we have. And you can see that these operations are all coherent. When we shine in the light, for example, on the carrier, this would be the black arrow that we see right here. And you see drawn is the population, and the D state is a function of the excitation time, and we see what we call Rabi flop. So it's a fully coherent operation which goes on a few hundred times. We can do the same thing on the sideband. Then, of course, we single out by spectroscopic tuning with a narrowband laser to the D1 transition. So we just add a photon, plus we add 1 phonon. That's 1 vibration. And that is much slower due to the fact that there's a modulation index involved, which we call sometimes lambda parameter, which is the ratio of the extension of the wave function in the ground state wave, the harmonic oscillator, which is typically a few nanometer, divided by the wavelengths of the exciting laser. So you see this is a few percent, and typically this is really a factor of 100 times smaller. That depends on the trap frequency that you have, but that's the typical time scales. All of these manipulations are done in a fully coherent fashion. And what do we do now? We take these operations, make sequences of single qubit and 2 qubit operations, and can do full-blown algorithms the way Dirac and Sola proposed it. So this is the basic way a quantum computer operates. And these gate operations are realized just with the carrier and the sideband transitions. We usually use both sidebands, but you could do it only with the blue sideband only if you like. And how do we analyze things? The analysis is, of course, always done by measuring how often the system resides in the excited state, so the populations, for example. And this can be measured, and the populations are usually typically cast in terms of density matrices, so we just analyze the system. But of course, we have not only a single particle, sometimes we have 2, 3, 4, 5 particles. So in order to see that we also the coherences, we just rotate the individual qubits, that's the Bloch sphere, prior to making a measurement, and then project everything. And you know, rotating, projecting, this is known in medical imaging as tomography. We call this state tomography. And this, likewise, we can actually analyze a full process. And there's also a spectroscopic way of making entanglement measurements via parity operations. I'll come back to that later. Just to give you a fingerprint, this would be the two particles, the fingerprint for a Bell state. You see, these are the populations, and these are the coherences, and the imaginary part should actually ideally vanish. This is how we analyze these systems. And this is one of the analysis that we took some time ago. This was the first generation of an 8-particle entangled state, which we at that time coined quantum byte. That took a while to analyze. It was not so difficult to generate it. The generation of that took several hundred microseconds. That was about it. But the analysis requires now to rotate each individual particle several times prior to making the measurements, and then to have to statistically average. In other words, we have about 6,500 settings, and each setting is measured 100 times. It took about 10 hours of uninterrupted measurement time for the quantum computer. But the difficulty was then to make sense out of these measurements, because what you really want to do is probabilities, is density matrix, which is semi-definite, which really means you have to have positive entries only. In other words, you have to fit the right density matrix to what the system really is measured. And sometimes the measurements give you negative entries, which is not physically meaningful. And that took first a few weeks, now it takes a weekend to analyze this on a cluster. This already points to the difficulty in quantum information processing. We could have done a 9th or a 10th ion, but the information which is required to describe it, handling this, is very hard already on a classical scale. So this shows what is a very important point when we just want to verify what the quantum computer actually does and validate what it does. This is not an easy task. We'll come back to that a little later. Then, over the last years, we have done many of these things. All of these things are done with certain fidelities. That's the overlap with what we want and what we ideally would actually have, would get. This is what we do. Single qubit operations work fine. And the more complicated these systems go, I don't go through the details here, the worse the fidelities got. And we had to trace it down, what is really making the fidelities worse in this system. Because if you really want to sustain a computation for a long while, you need so-called fault-tolerant operations, which needed fidelity which is way beyond 99.9%. Now we trace it simply back to the fact that during the Dirac-Sola operation, we not always ended up in the ground state. Remember, that was one of the conditions that went into the Dirac-Sola idea. And we could not prevent this. We never are ideal in our operations. The question is, can we find out a gate operation which is less sensitive to residual ground state excitations? And this is what we investigated. This was an idea that was put forward by Klaus Möllmer and Anders Sørensen. You see the people here, and was first measured in Dave Weinland's lab, and this work by Cass Sackett in 2000. What is the basic idea behind that? Instead of making individual addressing right here to individual ions, and the second one, and then do all the manipulations according to Dirac and Sola, Klaus and Anders came up with the following idea. If you just write down the system in the following way, suppose you had a blue super Bloch sphere, you consider now 2 ions sitting there, and of course they are labeled with the same quantum number n. And you have the same thing in the excited state. Then what you actually want to do as an entangling operation, this is what the C0 gate actually operation does, that would be making a superposition of these states and these states, and nothing in between. That would be ideal. Now if you write this down in a spectroscopic way, then you have to write down there's a possibility that we have one in the ground state and the other one in the excited state. Let's say with n-1 photons or n photons, this is a full spin ladder for the full harmonic oscillator ladder here, same way here. So in other words, if I just now treat the system in such a way that I make a bichromatic excitation, so I shine simultaneously in the sidebands on the red and the blue sideband, then there's 4 pathways through which the system can interact to make a superposition of these states. 2 photon transitions. But there's 4 amplitudes. What these guys did in this paper, they summed these amplitudes up and then figured out, okay, this sounds good, because all the residual dependencies on the n number here drops out. In other words, such a gate operation is first order independent in perturbation theory from the residual quantum number, which is exactly what we wanted to have. And the second is, we apply, this is something I didn't tell you about before, we apply, of course, frequencies which are symmetric about the center frequency. So residual stark shifts, which we always have in the Dirac-Sola idea, are not present, or at least suppressed to first order. And though the gate has a number of good ideas, let's make a long story short, how to measure this. Now this is again the same procedure that was figured out in the Davis group in this paper right here. They did Ramsey spectroscopy. If you just want to know about coherences, you do that, for example, in Ramsey's technique. You start out with pi/2 pulse of a single atom, and then at a later time, after waiting some time, you just start out with a second pi/2 pulse and change the phase. So the system progresses and develops, and once you have the right phase, the system turns up or turns down, depending on what the phase is. That's Ramsey spectroscopy. Now, if you just have a second ion and you want to know what this does, then you realize, of course, when I have the entanglement operation, this turns into a superposition of both ions in the ground state and both ions in the excited state, which really means I have these in lockstep. So this C0 gate operation, or the entangling operation, just puts the phase correlation between them. If I just measure now the same thing on the second one, without it didn't do anything here, then of course they should be correlated. So in other words, if I just now sum up how often I find the system in the even contributions, both up or down, and subtract from them the odd contributions, I get something which is called a parity signal, and you find the details in that paper up there. Make a long story short, what you can then see from the signal is that such a signal apparently starts to oscillate with twice the speed as it should have had if you had only, say, a single ion entangled or single ion in superposition, because the phase coherence is in lockstep. And from the visibility, you can immediately derive the fidelity of the operation. So we did this, and here is what we find out. If you just draw the probability of finding both ions in the excited state, ground state, both ions in the excited state, and these are the individual ions. So you just start this and you apply the bichromatic pulse lengths for a certain amount of time. And you see, initially, of course, all on the ground state, there's nothing in the excited state, and then there's nothing in the single excited state, but they develop, and at this time they're equal. And here, it drops out, so there's no first order contribution, according to Milner and Sørensen. So right here, we stop the system, and then we just measure our parity signal. The parity signal should give us now the amplitude, the fidelity, and you see immediately that should be relatively high. With a careful measurement, we figured out in those days, yes, the fidelity is beyond 99%, 99.3%. That was a good starting point to do this. And right now, we have improved on this with various measures without going to these details here. We have measures that point out that we, on the average, have 99.9%, and in certain cases, even beyond 99.9%, which is already then at the edge of being ready to fault tolerant. But I don't have the time to go into that right now. This is the state of the art as we have it these days. So this is really the idea to do this, at least in this case. But what's so important now for other physics is the following. What we actually do is the following. We just take these two ions, which is the gate operation, and talk immediately, of course, with the motion. The motion is always in the interleaved excited. So they talk to that mode. And if you really write down the mathematics, what you can do is then the effective Hamiltonian is nothing but a spin-spin interaction. Or two-level system interaction, spin-spin interaction. This can be written down. But now if you generalize this, take many ions, they talk to the same mode at the same time. In other words, this can be generalized as well, and that's a very funny Hamiltonian, because that is now a very generalized spin-spin interaction, which enables us to create so-called Greenberger-Horn-Zeilinger states all in one go, very complicated excitations, which you could do otherwise only by repeated biparticle excitations. And here is just how this works in principle. Remember, there's the two pathways that we had. If you start from 0, it's only 2. If you start from 1 or higher orders, then we have these 4 pathways. They conspire in such a way to give us a superposition, and the intermediate parts drop out. If you now have 2 particles, say 4 particles already, I'll drop the other ones, then you see there's more pathways. They interfere in such a way, if you just apply the system long enough, that you end up with a superposition of these. This is the GHZ states of many particles. Remember, these are the many interfering pathways that you have that speed the system up. That's the quantum parallelism at work. And you can do this with 8, and then it becomes really dense. This is what you have to control. You have to control a multi-beam path interferometer. There's nothing like a free lunch, of course. What you do is, in the computation, you have to be able to manipulate and control precisely a multi-beam path interferometer. Okay? So this works, and as a comparison, you see the Ramsey fringes for a single line excitation with the fidelity right here, and you see now how the speed up this works in a correlated way, even for 8, and we still have 82%, and even for 14, we have still entanglement here. It's different way of measuring. In other words, even with a single member Sorensen pulse, we are able to create entanglement of many particles in one go. So this is a resource for computation. This is what we have available. Now, this is a slightly different paradigm for computations than what we had before. Remember, the Dirac-Sola idea was simply a sequence of single and 2-qubit operations. What we have now at hand is the Wilmer-Sorensen gate operation, which can be generalized. They give many body entanglement at once. Then we have the resonant excitation, so we can do this with a global beam. We can all of them just turn up or turn down or tilt the Bloch vector at a certain angle, depending on the theta that we apply here. And we have also now pointed operations, that is individually at-rest operations, which are usually done now in an off-resonant way. So we just make off-resonant Stark shifts, which we just describe, of course, by a sigma z operator. So in other words, now for the more mathematically inclined people, we can write down the unitaries that we can apply with a Black application of the laser beams that we detune in certain cases. The local ones will be just the Stark shifts. You see the local Stark shifts right there. Then we have two global operations that will be either the collective Stark shifts when we are detuned, or collective rotations, or we call them collective yet local operations because we individually rotate the Bloch sphere of each particle, but they have nothing to do with each other. Or we do the conditional, or say the entangling operations. These are the spin-spin type. And this is written down in a more general notation because you can choose the phase with the lasers to select whether we just do this around the x or y axis. So we have many more operations available. And without going into further detail here, we have developed over the last 10 years also so-called hiding operations. We can reduce the computational subspace by just optical pumping the system to a certain part. I wouldn't say optical pumping, by just coherently manipulating them to a dark state. Then we have dephasing operations. Here we use optical pumping techniques to study open systems. We have initialization and reset operations. We even can implement a so-called quantum, what I call a quantum cache memory for a short time. So we have many of these things available. The basic set of operations is much more complicated than what we had before. So what we do is now we are replacing this paradigm of doing the computations that you've seen before with one that looks like this. We just have what we call a more than universal set of gate operations, and we have to select which way is the best one. I don't want to go into this. For this we have written compilers. We have optimizing compilers that select the best way of doing this, at least as to the best of our knowledge. And then we break down any algorithm that we want to implement in a sequence of these gate operations. And then we are ready to do quantum computations. And over the last years, we have implemented all of these ones that are highlighted here. So quantum Fourier transform, show algorithm, order finding, quantum error correction. I don't have the time to go through this. I just want to highlight these applications by two things that I personally find are a hot topic and that show you the power of these things by showing you, say, analog quantum simulations and digital quantum simulations. If you want to know more about these algorithms and more about this, I still refer you to that textbook. It's a bit dated right now, but it still is a wonderful summary of all of these basic technologies. So let's start with a simulator. A simulator, in principle, is nothing else but a system, a system that allows you to simulate the physics of a quantum system of interest by another system that's a lot easier to control or to measure. This could be done, for example, by finding similarities between the Hamiltonians that you want to use for the system and the one that you use for the simulator. So you just reinterpret some parameters. And so examples for this are, for example, when you just take, say, mod phase superfluid to a mod insulator phase transition. This is studied in these lattices and optical lattices with neutral atoms. Or you could use this at iron crystals. That was done by the group of Chris Monroe, by Tobias Schetz, and also by us. You see that in a minute. If you want to find out more about analog simulations, I will refer you to that one. Let me just show you how this works. And I would just highlight a little bit of the work that was done and guided by Christian Roos and Ben Lanyon in our lab. In this case, we just use ion chains as indicated here, but instead of the longitudinal operations, we use transverse harmonic oscillations. It doesn't really matter which ones. This is technically slightly easier for some reasons. So let's just use the transverse excitations. Suppose we start out with a chain as indicated here. This is indicated 7, could be 15, whatever, or more. And we do now the bichromatic excitations from the side. And the idea is to simulate now a Hamiltonian of the Ising type. And the Ising type Hamiltonian just shows a spin-spin interaction right here with these coupling matrices Ji, plus the transverse interaction with the interaction with the transverse magnetic field indicated here. Now, as was shown some time ago also by the group of Chris Monroe and others, you can actually recast these Jijs in terms of a power law dependent law, which can be roughly written as that. So in other words, we can simulate a system which has infinite range interactions. Remember, infinite range interactions with the ones that are simulated by the center of mass motion, for example, because that talks to everything at once. Or you could just, depending on how you formulate this, and I'll come back in a minute, you could do alpha equal 1, that would be Coulomb interactions, up to dipole-dipole interactions. And some of this stuff has been done also by Chris Monroe and others. I would like to concentrate, for the sake of simplicity here, on the case that we studied in more detail, is where this term is bigger than this one. So we just are in the case when you can rewrite this by the Pauli spin matrices in such a way that you recast this in the so-called hardcore hopping boson model. So you just have this exchange right here as in a hardcore boson model. But this is some technical thing. We could just reprogram it any time we really want to do that. And the system looks then as before. But now we just come up with the bichromatic beam from the side. So we just have this Jij coupling here. And then we still have the ability to have an address beam going to that if we really want to do that and detect the system as before. Why is this interesting? Now there was some work on spin chains. Suppose this is work by Philip Hauke and Luca Tagliacozzo for some time ago. Suppose you had a spin chain. They are talking here spin chains of about 100. And now suppose you just invert one of the spins, which is a magnetic moment. These magnetic moments talk to each other. Suppose this magnetic moment talks only to its neighbor. Then once you turn that, the next neighbor interaction simulates the magnet. Okay, I want to line up and pull it up too. And then the next one, next, and the next one. In other words, this spreads out like a light cone in the system. So this is what's predicted by nearest neighbor interaction. But if the interaction is longer range, then of course this should be behaving in a different way, because that already asks here, it talks to this one and this one before this actually the neighbor is seeing this. And if this long range interaction is very long, then there's interference patterns all over the field. And this just shows us how entanglement spreads, for example, in the system, and how magnetic excitation spread. So what we expect in this case, if you talk about group velocity, that here the group velocity becomes large, whereas here the group velocity is just dependent here on the system and the nearest neighbor interaction. Can we see this? And this was done in such a paper. So we just realized this, for example, here in this 7 spin chain. We just we prepared everything in the ground state, inverted the first one. Then we just let it spread out and try to measure things. And the point is here is just a mathematical description how we can realize these Jij couplings with the various Rabi frequencies and the frequencies that are going to the system. The details you find here in this paper by Ki-Wan Kim, who was at that time a postdoc in Chris Monroe's group. We just did it in the following way. We just hit all the ions and then we just measure the interactions between these. With this we can measure the entire Jij matrix. This is given here. And this really follows very nicely this power law dependence, as you can see. The circles are the power law dependence and the X's are the experimental data that we determined. So that seems to be perfectly fine. When we now make the experiment where we just start right here at time equals 0 with a spin chain of 7 ions, invert the first one and then apply the Ising Hamiltonian and let the system evolve, then you see that this spreads out. And then, of course, some reflections and then the revise right here and so forth. This is a pattern that appears. And then we can ask many questions. We can ask ourselves, how does entanglement really spread in the system? How does it propagate? What happens actually when I have 2 excitations? Do they collide? Or how do they just behave many body excitations, and so forth. You can study plenty of things. And the group of Chris Monroe, they really studied essentially how correlations behave, many body correlations. So this is a nice tool which allows to do manifold of measurements. Let me concentrate on a few things that were of interest to us. This was essentially how entanglement is created. You start out with 1 right there. Of course, here the system is not entangled. As you can see from the calculating the entropy, we have access to all of these degrees of freedom, so we can actually calculate that. Not only we can not only calculate, we can actually measure that and compare it. And you see, this is how entanglement is generated because of this coherent interaction. In other words, if we just now look, for example, for the spins right here, this one and that one, they should be correlated. And the correlation or the entanglement between the spins can be measured in terms of the so-called concurrence. This is a certain measure for entanglement. And we see how the concurrence really is excited and marches through the entire system. This would be spin 2 and 6. This would be 1 and 7. So we can really see spin waves of entanglement going through the entire system. And with this, we can do some complicated study, as for example, this was the nearest neighbor interaction closely related to 1.4. This is not exactly a 2 or 3. This is what we call the so-called Lieb-Robinson bound for nearest neighbor interaction. And then this is what you expect from the Lieb-Robinson bound. These are the white curves. But as soon as you have entanglement in the system, long-range interactions, this tilts down and the group velocity goes up. So this is a study that you can do, some simulation for quantum many-body behavior. And we could go on with that, but I don't want it. I just want to highlight some of these things right here. So let me just then turn over to the so-called digital quantum simulator. What do I mean with that one? Again, it's about simulation of a system that can be studied with another system that's easier to measure and to manipulate. But as opposed to the analog simulator, where we really try to replace, to sort of emulate the system right there, we now want to really calculate the behavior in terms of a digital implementation. That is to say, we make use of a full-blown quantum computer and the unitaries that I've shown you before. But the difficulty is now the following. Suppose you have the Hamiltonian system that you really want to simulate. So easily said, you would say, okay, I'll create now the unitary system, and my unitary system may break down into the key elements that I have and then do it simply. That's not quite so simple, because sometimes the underlying Hamiltonian the parts do not commute with each other. Then you either have to have the hard time, then you do this hard work analytically, but then the problem is solved anyway, or you would have to resort to some approximation. And that approximation is called the so-called Trotter-Suzuki approximation. What you do is you just use the individual parts right here, apply the corresponding unitaries that you have here, according to that formula piecewise, and then you just apply this only for a certain amount of time slice t divided by n, but then repeat the entire sequence n times. You can find more in this paper right here. Let me just show you how this works in a pictorial way. So we just take this sequence again of the more complicated Hamiltonian. We build each unitary from the pieces. Then we approximate this by the so-called Trotter-Suzuki approximation. And in a pictorial way, this really means we just apply this for a certain time slice, the next one for a certain time slice, and so forth. And then we repeat the entire sequence n times. And the higher n goes and the thinner the slices become, the better the approximation becomes. And this is sufficient for local quantum systems, as was shown here in the seminal paper by Seth Lloyd. Let me just illuminate this by just a toy system. Again, we take our two-spin Ising system, as it's written down here, with this J matrix is now just a J value right there, and then we have the interaction with the transverse magnetic field, as seen before. Now, remember, we can simply replace this with the unitaries that we have at hand. This with the basic unitaries that I've shown you. This is the Millman-Sørensen gate operation, and this is the Stark shift. Okay, now we know how to do this in a pictorial way. We just apply this, and then we study, for example, how often we find two ions up or two ions down, the two-level systems. And this can be done, we've measured. If we just make simple two slices, then you see the fidelity, and you see the marks over there. These are the experimental points, and the curves are the theory that you can easily calculate, of course, still for this toy problem. The fidelity is 69%. That's a lousy overlap. That's not very good, and you see this is failing. Now we make the time slices better. You see the overlap becomes much better, the fidelity is much better, and we hope for even better things. Yes, it works perfectly fine. And now we make yet finer slices. We can still do that. But then we find the same fidelity, and if you look closely right here, then you see there's deviations on the right-hand side. And the reason for that is already we have to apply so many gate operations that the quality, or say the fidelity of each individual gate operation is not sufficient to really give you the right result. So we'll run out of steam right here. And this is where we have to employ later on error correction if you ever come to the point. But this is something that is doable. So you see, actually, this is now a calculation of these things. The digital quantum simulation discriminates, is discriminated from an analog simulation, but the fact that you actually can estimate the error and you can undo the error in principle, which we have not done here. Whereas in an analog simulation, you cannot do error correction in the usual way. So this is just the underlying physics. And let me just show you in the last 3-4 minutes how this was recently applied for a problem which I really think is the first demonstration of what the quantum computer actually is good for in the future. And what we really wanted to do here, we wanted to tackle a problem which is hard to calculate on classical computers already, which is the quantum simulation of a lattice gauge theory, and we took the simplest theory that there is. The simplest way is the Schwinger problem. So we want to study how we can create, by applying a field, say a pair, and see how the pair is really entangled. This is a problem that is a model problem for lattice gauge theories, and we wanted to emulate this or simulate this with our quantum simulator. How do we do that? So essentially, as I said, this is nothing but QED in one dimension on a lattice, and we of course encode our particles, in other terms the fermions, in spins, or two-level systems, and the gauge fields, and that's something that was done by the theorists before we actually started, are transformed in long-range interactions. I don't have the time to show you how this is done. I can refer you to some papers here to how this works. But this was handed down to us by the theorists, and I'll show you the Hamiltonian in a minute. And then, of course, we simulate this in a universal way by stroboscopically approximating the system with a Trotter-Suzuki approximation. And what we really want to see, that the pair is created, and if you would go on, then other pairs are created, and so forth. And this was a minimal implementation with only 4 ions. But the 4 ions were actually encoded in a very sophisticated yet very clever way. And this is something which is not trivial, but this is also used in a clever way of programming this on classical computers. This is actually a so-called Wilson approach. What you do is you just take now advantage of the fact that, of course, you know what are even and what are odd sides in a computer. So we take the odd sides and say, okay, the odd sides should be only electrons, the even sides should be holes or positrons or the antimatter, and then we just say, okay, as soon as the ion is bright, this is a spin down. As soon as the ion is up, then it's a spin, as soon as the ion is dark, this is a spin up particle, and vice versa for the antiparticles. And then we can restrict, here is actually a reference to the theory article if you really want to look at that. Then we can restrict ourselves to the Hilbert space at hand. What's important for this is just the vacuum. We start with the vacuum, and then we create a particle and an antiparticle. Now, we denote our Hilbert space in such a way, we start out with a staggered space. The reason for that is a technical one, because a staggered space is nearly what we call decoherence-free subspace, so we do not worry too much about decoherence in the system. But that's something we can do. This is a notation. Then we denote all these subsequent elements that are necessary to study the Hilbert space, and these are the particles that we possibly can create. And pair creation is then the process where we just go from this state to that state, where we create a pair in the middle, because we also want to investigate entanglement, and I'll come back to that after a while. So this would be that state. And states outside this Hilbert space, this we can, of course, restrict ourselves to. This is post-selection in the measurement. This is considered unphysical, which we are allowed to. Now, this is the Hamiltonian that was handed down to us that consists of a long-range interaction, and the CIJs, they were actually the hard part to program. According to the theorists, we had to do this in an asymmetric way. Then we had the hopping term of the particle and antiparticle creation, and we had some mass terms right here, and they come also from the transformation. This is a longer story. This comes handed down here from the author in this paper right here, but this is proven and can be done. And then we have also the coupling constants right here, the lattice spacing and the particle mass. And then we had to just, in quotation marks, make sure that we can tailor CIJs with the appropriate Mercerns and gate operations that we have there in an asymmetric way. This can be done because the problem is known when you have the Hilbert, the Hamilton, and then we can just rearrange these things, and then we can break this down in a sequence of these unitaries. And then, of course, the recipe comes as before. We just take our trotter series. This is the individual trotter step consisting of these 3 different Hamiltonian parts, and then we just repeat this over and over again. So this is the implementation with the various coefficients, and this is the asymmetric part of the Zij's. It comes down to this, so that the entire program after an initialization sequence, which prepares the vacuum state, looks like this. But this is to be repeated 4 times, so this is a total of about 220 gate operations that we have here, and of course we have to have a trailing operation in order to then prepare things for a measurement. To make a long story short, this is the outcome. We draw here the particle number density that we create as a function of the interaction. Strength and time, this is a renormalized time period here. Then the theoretical part would be the green one, which we still can calculate for this simple problem. Then the next one is, of course, what is the experimental data? The experimental data are the ones with the error bars. You see the ones? The error bars are relatively small. Then the point is, what are the discretization errors that we actually have to take into account? And they can be calculated, as I said, for any Totta-Suzuki approximation. This can be done. These are the red curves. They seem to sort of agree with what we see here already. And then we have a deviation. And then we still have to make sure that we have other errors in the system, some dephasing, some global dephasing, taken into account. This is our error model. And these systems seem to agree. But what you see here essentially, it's essentially a study where we start from the vacuum state, that's the one that we see here, and end up right here with this state where we create a particle. It looks awfully like a complicated Rabi flop. It's nothing else. But the point simply is it's just the reinterpretation of these things. But you reset the system in such a way that your parameters, like the masses, the interaction constants, and everything else, goes into the Rabi frequencies and the tunings that you have to measure carefully. So this is the pair creation that we can demonstrate in the predicted way, and we can do this in a more detailed way. Details don't matter right here. More important is that you can also create and you can actually measure the entanglement in such a system, because out of the vacuum, it's a point-like interaction. You create a pair. Of course, this pair is highly entangled. You can now measure that, not only just produce it, you can measure it, and this is again measured by the entanglement. Here in this case, it's not the concurrence, but the logarithmic negativity, another way of measuring this, and this is what we do. I'm at the end of my time. Let me briefly summarize and sum this up. This is now a very complicated application, but it shows you already a taste of what can be done with these simulations. We need to scale this up, and David is going to talk more about these things. There's various things that we also pursue, like cavity QED, using photons to create interfaces. There's dipole-dipole coupling. David is going to talk about this trap arrays and things like this. There's these special trap designs. David has come up with some in 2002. And everybody in the field is now also developing these segmented traps. David is going to talk more about these. And we have also these traps in our system. And the idea here is really to do something like Star Wars on a chip. So you just fire laser beams and have the particles move back and forth, an idea that was put forward by these two gentlemen, and I'm sure that David is going to talk about this. So let me summarize the things. I've briefly shown you why and how we do a quantum computer with these calcium ions that we have, and I showed you just aside from the quantum toolbox, a few things that we do with that, and of course, the future I personally think is still bright. There's many things that we still can do with that. But of course, there's many things that we need to do. My dream and the vision for that is that we get now locally encoded logical qubits, which really require more than one qubit to do it. And then we implement error correction to protect the system. And of course, then we just extend this by dipole-dipole interaction, maybe on a chip, or ion cavity interfaces in a network. So which really means we can go later on then to strings, as you've seen before, 40, we actually have 50 ions and 70 ions in the system. We can control right now up to about 20 in a full-blown way. We can control up to 50 for analog quantum simulation, but we cannot control the 50 yet in a universal way. There's many things. In the end, what it all boils down to, we need to keep the qubit alive, at least for the computation. That is what I personally think is the holy grail of the entire field. That's still very, very hard, but the good message is, as far as I can see, there's no physics roadblock in sight. It's not just technology, because there's always physics that can supersede technology, but it's a lot of work to do still. But once this is done, then we can all do the rest, I think, in a lot easier way. With this, I'm ready. Of course, this is done by a large team that we have here, and of course by a large team of theorists that help us do that, and of course by many funding agencies who just put in their money. Thanks very much for your attention.
Thank you very much, Rainer. Are there questions about? Oh, Christophe.
I have a question on the trotter expansion.
Yes.
Where you split your Hamiltonian in small pieces and time in small pieces. How does it scale? You've taken two items. I don't mean the trotter expansion simulate. You had a theory curve that was on the result.
No, we had for the trotter expansion, for the first one, that was just the toy experiment. But for the later experiment, you had 4, yes, and you can make more ions. See, the point simply is the trotter expansion is of course especially useful when we have these highly non-local operations, when we have these Milnor-Sørensen gate interactions that entangle all spins at once. That really makes it useful. Now the question really is, what is a better way of scaling things up? Making, say, entangling operations between all of them and avoid having those who don't want to entangle taken out of the system by hiding operations, or make, say, controlled Milnor-Sørensen operations on only those that you want to do. That is the technical question. But I think otherwise the trotter scales in a polynomial way. There's no exponential over it.
Yeah, but experimentally, what is the limit? I mean, if you want to...
the limit is always
the dynamics, because it really applies to the dynamics of the system.
Absolutely. No, the figure of merit is, okay, first of all, how many qubits do you have, and how many gate operations can you do? So this is the product space that you have. Right now, we have about, say, if you can do 4 to 8 ions with the new gate fidelity is about 400 to 500 gate operations. That's typically the product. If I have fewer ions, I can do a few more gate operations because they stay still fine. If I have more ions, I can do less. So this, the product is roughly the figure of merit. And this scales with the fidelity of the individual operations. And then, of course, you have to take into account what is the trotter error that I can take into account, depending to which degree do I want to follow the dynamics. What is the resolution that I want to have? If I just have a gapped system and the frequencies are so far apart that I just need to see the gap, it's fine. But if I have, say, a closely spaced systems like a many-body Hamiltonian, we have some of these, then you can't do it, at least. Then you would have to go to such fine slices that you don't do it. So it very much depends. I cannot give you a general rule, but the overhead scales, not exponential, the overhead scales polynomial.
Okay, when Serge?
Yes. Yes, the fidelity with 4 qubits is, at this time, it's 98.4%, and we still can improve on that. Now the question really is, do we need a fidelity, say, of 8 qubits of 99.9% to entangle them? The answer is no. In principle, it suffices to have, say, 99.9% between 2, because then it boils back again to the fact that you have an entangling operation and single qubit operations, and you can do a universal operation. But you forgo, of course, the possibility of making very elegant solutions to complicated problems. So you really have to break it down again in 2 particle operations. But once they're good enough, then the advantage would be that you could possibly invoke fault-tolerant computations. So you have to do a bit more error correction in the end, but you could do it. So it's not as elegant as it would be with these, say, highly entangling operations. N-body entangling operations are, personally, I find them brilliant. But if I can't do them well enough, they are useless. So I have to break it down into ones I can. So it's not a roadblock. It helps. We will certainly improve that as much as we can, but I do not know exactly how this scales. So for example, for 4 ions, we have nearly the fidelity as we have with 2, But when we have 8, and this has something to do with the optics and technical things here, then this falls off much faster than I thought than it's supposed to be. So it's a bit a tricky question.
So we are running away of time, so short question.
Yes, short question. Just about your last point, keeping your qubit alive. So how long you want to keep it alive?
For the entire computation, not more.
So usually, usually how would you do it? I mean, seconds or
No, right now the coherence time of the system is typically on the order of about 100 to 200 milliseconds. That's what we have. Now, some people talk about the eternal qubit. I don't, because that's an illusion, that's a vision, that's very nice. But of course, what we want to do is we want to keep the entire computation fixed,
so
which really means
on your computation.
these gate operations say until we would need error correction last on the order of about a millisecond or 2. So, but the coherence time is already much longer. But the fidelity is not good enough to sustain the system. But so if, for instance, if we had, say, for a millisecond or 2 milliseconds, an operation, which is already a complicated operation, and then we would have to do error correction. Unfortunately, that error correction would take a lot of time to do, but then we could carry on. So this is all we need.
Okay. Okay, so I think we have to thank Rainer again.